Hello, Paul Watts here. High Flying Physics, supporting A-level physics students getting top grades. We're going to have another look at a question today on equilibrium. It's a classic question involving calculating perpendicular distances, moments, and also resolving forces. Let's take a look at it. Okay, we've got a uniform rod of length 1.5 meters and of weight 300 newtons. It's hinged from a ceiling and held off to one side by a horizontal force F acting at the lower end 0.8 meters below the ceiling, as shown in the diagram. And you've got to calculate the size of that force F, calculate the magnitude of the vertical and horizontal forces acting on the rod from the hinge, and calculate the magnitude of the resultant force of the hinge on the rod. Okay, so let's just take a look at the forces again. So we've obviously got our force acting to the right. We've got our vertical force of weight acting in the centre of our rod. Without the hinge, the weight of the rod would cause the whole rod to accelerate downwards. But because the rod is in equilibrium, there must be a vertical force from the hinge holding it upwards. There we are, we'll call that HV. Also, without the hinge, the force F acting to the right would make the whole rod accelerate off to the right. So the hinge must be providing an equal and opposite force to that, and you can see that marked there as HH. So there's our rod, and those are all the forces now acting on the rod. We know that our rod is in equilibrium, so therefore we know that we can take moments from any point, and we know the clockwise moments are going to equal the anti-clockwise moments. Now, it's always a good idea when doing these sorts of problems that you take moments from a point where you've got a number of unknown forces. If we were to take moments in this situation about the hinge, it means that in our equation that we're going to end up with, those unknown forces at the hinge won't appear in the equation. So if we take our moments about the hinge in that case, we can say the anti-clockwise moments are going to equal the clockwise moments. Force F is providing the anti-clockwise moments. Now, the moment of force F is obviously the size of the force times the perpendicular distance. To work out the perpendicular distance of that force to the hinge, as you would have seen from the previous equilibrium video, you extend the line of the force, as shown there with that red dotted line, and then you draw a line from the hinge to the line of the force that cuts the line of the force at right angles, as shown there. And we know that from the information we're given in the question that that's 0.8 meters. The 300 Newton force is providing the clockwise moment. So in order to work out the clockwise moment from that 300 Newton force, we need to work out its perpendicular distance to the hinge. So again, what we're going to do is we're going to extend the line of our force, and then we're going to draw a line from the hinge to the line of the force that cuts the line of the force at right angles. Now, in order to work out the length of that perpendicular distance, there's obviously lots of different ways of doing it. I'm simply going to work out the length of this distance of the lower side of this triangle, because I've got the other two sides there, 0.8 and 1.5 meters, and therefore by using Pythagoras I can work out that that is 1.3 meters, and our perpendicular distance is going to be half that length, which is going to end up there, as you can see there, is 0.65 meters. So going back to our equation then, anti-clockwise moments is equal to clockwise moments. So our anti-clockwise moments is our force times the perpendicular distance, which we've just shown is 0.8, times the clockwise moments, which is our 300 Newton weight, times its perpendicular distance from the hinge, which we've just calculated as being 0.65 meters. And reorganizing that and doing the calculation, we can find that F is equal to 244 newtons. Okay, part B, calculate the magnitudes of the vertical and horizontal forces acting on the rod from the hinge. So here are our forces again, and the force off to the right now that we've just calculated is 244 newtons. We also know that we've got the vertical force from the hinge acting upwards, which we're going to call HV. And our horizontal force, HH, which we don't know, is acting off to the left. If we resolve vertically, we know we've only got one force acting upwards, and we know we've only got one force acting downwards. We know it's an equilibrium, so we can say the forces acting up must equal the forces acting downwards. So HV is equal to the only force acting downwards, which is a 300 Newton weight. Resolving horizontally, we can say because it's in equilibrium, the forces acting to the left must equal the forces acting to the right. Well, we know of the forces acting to the right, and there's only one of them, and that's 244 that we calculated in part A. Therefore, the hinge horizontal force, HH, must be equal to 244. Finally then, in part C, we've got to find out the magnitude of the resultant force on the hinge on the rod. That's fairly straightforward. You can see what we do there. We draw a rectangle around our forces like that. At that point, we draw a diagonal line, and that is the force, the resultant force that we're interested in. And we simply apply a little bit of simple Pythagoras, which you all know how to do, and that comes out to be 387 newtons. Good. I hope you found that useful, and see you soon. Thanks. Bye.